All right, can you see my screen?
Yes.
Great, that's good to know. Okay, so all right, let's get started. Thank you so much for joining us to our user training webinar series. We're very happy to see that I think we already have like more than 10 users, 10 people joining us today. So before I get started to our session, I would like just to give a quick overview of our webinar series and the following sessions and another exciting announcement to share with everyone. So to get started, my name is Jay Wang. I'm currently a research assistant professor at Iowa State University, associated with our YSI Center. So here you can see what we're showing is we have already arranged 4 sessions, free and open to all. For anyone who's interested in our testbed and how to use it, we have arranged 4 sessions focusing on different topics, including MIMO, SDR, COTS, 5G, and RX Hall. So, and today we're going to focus on AraMIMO. So if any of these sessions can be of interest to you, feel free to sign up today. We have prepared a QR code on the left side. And after this session, you're like, okay, I missed the QR code. Feel free to reach out to us as well. All right, so another exciting announcement is that we have also arranged a YSI webinar, and the title could be very exciting. I feel like to a lot of people who have worked with our testbed. So the title would be teleoperating autonomous vehicles using commercial 5G networks. So what would be the status? So the speaker would be Professor Zhili Zhang, who's a distinguished professor from University of Minnesota. And then this webinar will be held online next Wednesday, March 4th. So feel free to also register today. It is also free and open to us all. So we have also prepared another QR code on the right if you are interested to attend. All right, so I will keep it here just for a second while we also introduce our speaker, Taimur, here today, and I'm very excited to do that. Taimur is a PhD candidate in computer engineering at our YSI Center at Iowa State University. He has received his bachelor and a master degree in electrical engineering from the National University of Sciences and Technology, or short as NUST. That will be in 2014 and 2020, respectively. And before joining YSI, he has gained over 6 years of industry experience. And after joining YSI, he has worked on like multiple topics around wireless networking, including MIMO, Open RAN, 5G, 6G wireless systems, URLC as well. So without further ado, I would like to give the floor back to our speaker, Taimur, today, and we'll get started on our training session.
Yeah. Thank you, Jay. Thank you for the introduction. So I will share my screen. Can you see my screen?
Yes.
Okay. So thank you everyone for joining today. So today's webinar, as introduced by Jay, it's on one of our platform, AraMIMO, which is a programmable TU whitespace massive MIMO living lab for rural wireless. Myself, I'm Taimur Islam, and I'm a graduate research assistant working at Center for Wireless Communities and Innovation. So today's So here's the brief outline. So we will talk about the rural broadband challenge first and what opportunities it has to offer. And then we will talk about the need for this testbed, the Era Wireless Living Lab. And then we will talk about the AraMIMO TU Whitespace, which this particular webinar is about. And then we will have kind of a live demo, how to do experiments with this platform. And then I will share some of the performance characterization results and some of the demo experiments. And then at the end, we will share some of the resources with you, which you can use, which basically you can use to use this testbed for your experiments or your research. So Let's talk about the rural broadband challenge first. So, the rural US constitutes about 72% of the nation lands, inhabited by 46 million people. And 39% of the rural US, which consists of mostly agriculture farms, lack access to the broadband internet. And over 3 billion people worldwide basically have no access to broadband services. On the other hand, broadband itself is evolving at fast pace, specifically in urban areas, which has resulted in perpetual rural-urban broadband divide. Um, on the other hand, the rural areas itself offers a lot of applications and opportunities. And there are a lot of rich and diverse use cases. For example, camera crop phenotyping, or AR VR applications, grain mill for system control, and then basically some of the Internet of Things stuff. For example, the grain bin or livestock health monitoring, etc. So all these applications gives a really good rural first advantage in piloting high impact applications. Um, so if having all these applications in rural areas, why it is still a challenge actually? That's one of the question, basically, and the answer to that is the lack of rural-focused wireless innovation. So, over the years, basically, the research and the innovation or the advancement has been focused on urban areas to ensure more capacity in general. So that's why basically the rural areas remain behind. So how can we enable this rural-focused wireless innovation? The answer is Era Wireless Living Lab that we are going to talk about now. So Era Wireless Living Lab, it's deployed in central Iowa. So here you can see the map actually. We have a number of different sites. So we have 7 base stations deployed so far. So on the green ones here, basically you can see the green ones, actually they were deployed in phase 1. And then the yellow ones that you can see, they were deployed as part of phase 2. And now we are deploying this new site, Info Bunker, that will be ready by the start of summer. And we have about 34 UEs deployed in the vicinity of all these base stations. And there are more UEs to be deployed soon. Here you can see some of the glimpses. So the Wilson Hall base station, it's on the rooftop on one of the a residential building. Here you can see the antennas actually deployed on a rooftop. And other 2-3 sites basically of phase 1, the Ag Farm, Curtis Farm, they are monopole sites actually. And then there is Research Park, which is also rooftop. And then in phase 2, basically, there are public safety and education towers, Boone, Gilbert, and I6. So our the platforms are deployed on these towers. The UEs are very diverse. They are deployed on buses, on ag vehicles, water towers, crop farms, residential customers, agrobot, and then some of the biorefinery or feed mills. So here is the Era system architecture. We have device stratum, edge stratum, and cloud stratum. So at the device stratum, the applications on which basically the UEs are deployed. So they interface with our UE station. So at the UE, we have different types of UE radios. So the SDR, MIMO, and the cards. In the subsequent webinars, we will be talking about the other ones. Other ones as well. And at the edge stratum, we have the X Hall, the wireless X Hall platforms, and some of the RAN platforms, as well as some of the edge servers and other equipment deployed at the edge stratum. And the cloud stratum, we have controller devices, storage nodes, compute nodes. And for the operation of the test bed, actually, we have the monitoring, CI/CD, and other servers actually that are deployed as part of the cloud stratum. So In today's session, we will be focusing on this part of the system, which is the AraMIMO TU white space. So at the UE side, we have one CPE deployed, and at the base station, we have the the wireless platform deployed, which is from Skylark Wireless. So regarding the software architecture, Era is based on OpenStack. So we built it on top of OpenStack, and we extended its capabilities to manage the wireless resources. For that, basically, we have resource managers and container managers actually running at each of the nodes, actually at the controller and also at the base station and UE sides. And the resource manager basically help with the lease, the resource reservations and stuff. And then basically the container manager help launch the containers on top of those resources, those compute nodes. At the base station side and at the UE side, we can see that we also have kind of the container managers running there. And on top of those, container managers, we have the containers running the experiments. So this is how the software architecture looks like. And the user kind of log into the portal, and then they reserve the resources at the base station and at the UE sites, and then they launch their containers on top of those nodes, and then they run their experiments. So this is a kind of, the overall overview of the software architecture. And there are some other nodes, there are some other services like the wireless guard, error monitoring, fault tolerance. Those are mainly for operating the test bed and then making sure that it is always available, and for spectrum enforcement policies, etc. So the Era Wireless Living Lab consists of many wireless platforms. So the RAN platforms, actually, we can see them here. We have the AraMIMO TU Whitespace, and then that is based on the Skylark Wireless. It operates at the low UHF band. Then we have the Ericsson platforms, that operates in C-band and millimeter wave band. And then we have the SGR platform that also operate in the mid-band. And then we have the Era Hall platforms. So we have the microwave, millimeter wave, free space optical, and also low Earth orbit satellite links used for as Era Hall platforms. So again, today we will be focusing on AraMIMO TU Whitespace platform that operates at low UHF frequency. And next, we will start talking about this particular platform. So we have 4 base stations deployed, actually. So on the previous slides, you saw some of the glimpses, actually, right, of the actual deployment. So we have deployed it at Wilson Hall, Gilbert, I6, and Boone towers. Each base station has 3 sectors. So here we can see the radio units, the RU, actually. So there are 7 radios. Each radio has a dual polarized antenna, which makes it 14 antennas per sector. Here we can see 2 sectors, but there is another sector on the other side of this platform. So there are 3 sectors per base station, which translates to a total of 42 base station antennas. And on the same rooftop, we have the DU and some other equipment for power and for fiber deployed there. And then we have 24 UEs, 24 the Skylark UEs, actually, which has this Skylark platform deployed. So here we can see kind of the Skylark CPE and the antenna. It's more clear in this picture. So we have the CPE radio, and then we have the dual polarized antenna. So we have 2 channels, horizontal polarized and vertical polarized for each UE. And these UEs basically range from 1 to up to 5 miles, different distances from the base station. The compute nodes are in the cabinets or in the kind of small boxes, actually. And then the radios are deployed outside. So how basically this platform enables the experimentation. So we have 2 different types of APIs. So the first one, we call them wrapper APIs. So for that, we have the cloud, actually, that we saw in the system architecture. So the user actually access the portal from the portal, they can reserve the resource actually, and then they launch the container. So we have a compute node at kind of at the base station side. The user launched their container here. That container has a local bridge or MAC VLAN interface to the compute nodes actually. And the compute node itself is running an API server, which is making RPC calls to the PHY application on the Skylark CU. So that's how we expose the system to the users. Actually, the users are restricted to the container itself, but the capabilities are kind of like exposed to the container using this architecture. And it makes it restricted so that it is only the experiment launched on a particular node can be performed on that node only, and not like any other nodes. The other ones are the modding APIs. So they are they provide more programmability actually. And in this one, kind of, we can see that, so this is on the left is the Skylark application modules. And here on the right, we have the modding library modules. So here what the system do is that when the uplink pilots are received at the base station, they are like handed over to the modding library, and here basically the user can define their own like scheduling or user grouping or MCS selection algorithms, and then send back the schedule back to the Skylark application to schedule the UEs in the downlink. So this is like more control and this needs direct access to the CU. So this is not kind of like publicly available yet, but if you think it's useful for you, or I mean it will help your use case, your particular research, you can reach out to us, and then we can work with you to make it accessible to you, and then you can use them for your research. So now we will move on towards the live demo actually. So before starting the live demo, kind of here is the pipeline. So the user basically logs into our portal. So you will create in your account and everything actually, and then once the accounts are created, you will log into the portal. Then a user can reserve a resource. And then once the resource is reserved, we can launch a container on top of it. And then we will kind of run our experiment. Actually, we will show like some basic commands today. And then we will have our experiment container after the data collection deleted, then the resources released, and then the user logs out. So this is kind of a general flow actually of the demo actually. Let me pull up my just a second. Okay, so I'm sharing my screen actually. So here is the portal.arawireless.org. So once you log in to the portal, actually, this is how it looks like. We have the resource overview. It shows like all the nodes that are available for experimentations. We have like many nodes. There are AraHall nodes. There are a lot of nodes in the sandbox. We have the Skylark, Ericsson base stations. So we will go ahead and reserve our resource first. So here we can see that we don't have any leases as of yet. Here is a host calendar where you can see kind of, which nodes are available and which are not. So some of these nodes have been reserved by users and some experiments are going on. And the rest basically are available. So we will go ahead and then click on create lease. And then we will choose a name. So I will choose SKLK lease 1. We can specify the start date and end date as well in UTC format actually, but I will leave it blank. So I mean, by default, it will allow me like a reservation for 5 hours starting like immediately. And in the resources, I will select Wilson Hall. we have to select the resource type. So we are doing an experiment with AraRAN, and then we are choosing the Skylark base station, and the device ID we are using 0. So all this, this whole process is documented in our user manual. If you go to our user manual here, so this is kind of the basically our user manual, and it is everything is documented here. So I will come back to it just to show some like part of it that you can follow for these experiments. And then we will create the lease. So right now the status, it is showing pending. So we will wait for it to change the status. So it is starting now and it is active. So once the lease is active, we will go to create our container. So I'm going into the containers tab. I will click on create container, and then I will choose a name. So I'm choosing SKLK_MIMO. And here is the image that I'm selecting. Again, this is documented in our user manual. So this is the image that is going to be used for this experiment. And then we want our container to start running after we start. So I will just run bash actually when it starts. And then we will choose our lease name. So this is the only lease I created. So that's it's showing up here. Then we will click next. And then we can like choose the network. So I'm seeing two networks, but I mean your view could be different. So I will basically connect it to one of the common network actually. So it's called the shared network. And then I will go ahead and create the container. So the state is showing creating, and yeah, immediately it's running now. So the status is running. We can go into the container. Here, actually, it is showing us some of the information about this container. Here we can, once we start working with the container, actually the logs are created here. And here is a console available within the web page, actually. So this is kind of, we are in the container now, and this is actually launched on the compute node that I was showing in the architecture. So here we can launch the Era SKLK CLI. So here, these are the APIs that I was talking about in the architecture. So these are kind of exposed APIs so far. So if I write help, there are a number of commands actually available. So for example, I can do get connected UEs. For example, I can run this command, and then it will show me that we have like some UEs connected already. Actually, I can do get UE stats, and then it will show me some of, so like there are 3 UEs connected right now, so they are showing the serial numbers here for both downlink and uplink. So this is the downlink. The first row is for the downlink, the second row is for the uplink for each of the UE. We can see the the bus rates actually. So the bus rate is actually how much capacity the link can achieve. So it is derived from the SNRs. The SNRs are also available actually, and then there are some other stats actually that are available for this. The serial numbers, kind of, we can see the get UE locations, for example. So this is showing us that this one is FL1B00011 is, for example, the AIMS UE000. So the AIMS UE000, if you want to see where it is, basically you can see it on the Era Wireless Living Lab like deployment as well. So for example, this is the kind of the like the live map actually. So here is the UE deployment. This is the whole Era deployment. You can see the base station and the UEs. And then if we log in here, this is the AIMS UE00, and we have the experiment launch from like at the Wilson Hall base station. So this way you can see like which UE is connected, which is not. And I mean, you can actually reserve these UEs as well for your experiments. So this is kind of just like a basic experiment. I can quit from the CLI here. There is a public repo actually with all the APIs available in this container. So if you go into that repo and then I do ls, there are some scripts. For example, you can capture the CSI, you can capture the KPI data, you can capture the latency. So these are some of the example experiments that are given. And then we have a public repo actually, right? Which this is like these all these APIs are based on. So here you can see a bit of the documentation and also kind of what these scripts are and what they are doing. And then on top of that, basically you can write your own scripts for your experiments. So this is kind of the just a quick live demo. Here is the like the overview page again. Basically, we use the console, but within that, like the experiments and the documentation, we have like explained it if you how you can SSH into this container, right, from the Era jump box using this floating IP address. So you can work within the console, but it's a lot easier if you SSH into the container instead of working in the console, because it gets closed and then you have to refresh it every time. This is just like kind of providing some basic functionality, but if you SSH into the container, you can do a lot more with that. So this is kind of just a quick live demo. We can stop and delete our container. Let's say we have collected our data, we have stored our data, and then we will just, if the experiment is over, we can just delete our container or delete our lease. If we don't do it, actually, like after 5 hours, it will be deleted. The system will delete it itself. But this is just to make it available for the other users, actually. It's a good practice to delete the container and the reservation. So here is the user manual. Actually, if you want to do the same experiment, you can go to our user manual. It's erawireless.readthedocs.io. I will share at the end of the presentation some of the resources actually. So this actually covers like the overview, getting started, the technical manual, the experiments, the API references. So for this particular live demo, this was from the AraRAN experiments. So in the AraRAN experiments, there are like the open source NextG, the ORAN experiments, and the massive MIMO. So I followed this first experiment, actually monitoring AraMIMO wireless link behavior. So here you can see kind of it's giving you the architecture, and then there are like steps how to log in. There are some notes. Actually, you can do the hello world experiments first, and then it is like specifying the Wilson Hall AraRAN. The stuff that I selected during the experiments, what device ID you can use, and then the commands that you can run actually, and how it will look like. So this is just like a brief kind of live demo that I wanted to share during this session. So yeah, back to our presentation. So these are the steps that we followed actually. So I didn't log out, but we can log out from the portal as well. So this is the step that you can follow the experiments actually in our user experiment and at the user manual. So yeah, these are the 3 experiments actually for the MIMO that are available on our user manual. And those are basically related to the CSI capture, or just like the basic KPI capture. Or if you want to perform an experiment at the UE side. So these are the experiment that we followed. But there are other availables. We will have like following webinars actually that will cover some of the more experiments as well. Regarding the programmability and measurement, so this is a production grade system based on Skylark Wireless, operating at low UHF, and we can, using the modding APIs, we can have our scheduling or user grouping algorithms. Using the wrapper APIs, we can select the MIMO layers, the frequency selection, change the bandwidth, the filter paths, the uplink, downlink frames, the MCS. We can do all this kind of stuff with this platform actually, change it, and then we can measure kind of some of the KPIs, the SNRs, the throughput, latency, user grouping information, and for example the multi-cell interference. So these are some of the capabilities actually of this system. Now, using the same APIs actually, right, that we have built, we did kind of some of the performance characterization of the system and some demo experiments that I will go over next. So system, basically kind of the Wilson Hall base station. These results are just for one sector. So this is the south sector connected to, there are 6 users connected. And it is operating at 563 megahertz, and we can see that it achieved up to 350 mbps, different users achieved like different capacity depending on how far they are, how is the terrain, and the environment, etc. And then for each user, actually, we can see that some user are getting more, actually. So for example, this particular user, the UE4, got higher capacity up to 80 Mbps. Some of the others basically got lower capacity. So it depends on basically how far and where they are in the sector, actually. And then we have the latency characterization. So again, like each UE has a different latency profile. So on the average, kind of the system is like achieving 16 millisecond latency one way, like for each of the UEs, and it is varying between 15 to 17 milliseconds. So these are some performance results from one sector only, right, across the 4 base stations. And the next experiment is on the user grouping. So what we did is we connected different sets of UEs. So on the map that I was showing, actually we had the UEs there. So we chose like 4 UEs, right, in each set, actually. And then what we did was that, in set 0, basically we connected all the 7 UEs. So here in the map, you can see this is the base station, and there are like 6 UEs in one sector, and then this and like UE7 is in another sector. So if we connect all the UEs together, like that achieves the maximum capacity that is up to 400 Mbps, actually, since we have like 7 users. This is the blue curve is showing is if the default user grouping algorithm is used by the system, it will achieve 400 Mbps. If we force all the UEs to be in the same group all the time, actually, then it achieves lower capacity, right? Because like they are not spatially like fully orthogonal, so they will result in interference, and that's why basically the capacity will reduce. Similarly, we connected like only 4 UEs. So we connected UE 1, 2, 5, and 6, or 1, 2, 3, and 4, actually. So 1, 2, 3, 4 has better spatial resolution, actually. So we have 1, 2 here, and then 3, 4 are kind of like very far from there, right? So the user grouping algorithm can better like achieve better orthogonality. So that's why it is achieving higher capacity than the UEs that are packed together in like 1, 2, 3, 4, actually. So they are packed 1, 2, 5, and 6. That are packed together in one area, actually. So then the capacity is lower for that. So similarly, we did like some other configuration. So this is just an example experiment, and this shows us that the right user grouping algorithm or the user scheduling basically can achieve like better performance with the system. Then basically we also showed that like for these different sets of UEs, actually we can see that for the set 0, actually, which is like the 7 UEs, right? So it can like it can group up to 6 UEs, 6 streams, actually 6 layers. But while set 1 can do like up to 4, and set 2 can do up to 6. It's basically just because of the special like orthogonality achieved. Then this one is this plot is showing the orthogonality. So again, basically for UE set 0, if we can, with the APIs, basically we can force the system to use 3 layers or 4 layers or 5 layers or 6 layers, actually. So that's programmable. So if we kind of force the system, basically, we can see that if we try to, like say the black one, actually, right? So it is showing all streams grouped together. So if we force all the streams together, basically, then it achieves lower orthogonality. But if we group only 3 streams per like three streams or like 3 layers, actually, then it has the highest orthogonality achieved. So these are some results basically from the grouping experiments, and that's something that you can do, right, with the system. Next, basically, we also collected some of the data during different like rainy and like snowy weather. So here we wanted to see the correlation between the like the channels actually. So as I explained, we have like three sectors. So three sectors, we have like 42 antennas actually. And this is basically, since one of the sector was facing the UE, so it is basically showing the correlation for those only. So here we can see this on the left one, basically we have the before snow and before rain actually. And on the right side, we can see the during snow and during rain. So we can observe that during the snow or during the rain, actually there is lower correlation in between the channels actually. So from each UE, basically there will be 14 channels to one sector because the base station is having 14 antennas. So then it is showing kind of that correlation between the channels. So if we have lower correlation, perhaps that can be used like for mMIMO gains actually. So we studied this in a different study, in a different research. Basically, it's not shown here, but this is kind of just showing that these lower correlation values can help basically compensate for the additional losses that comes with the snowy or the rainy weather. Next, we since we have like multiple base stations, actually we wanted to see the impact of interference of one base station over the other. So here, two base stations are operating at the same frequency, and they are not coordinating with each other. We chose like two UEs, right, from this base station. So we call it the Curtis UE and the Sheep Farm UE. It is deployed in the sheep farm. And here, basically at the I6 base station, we selected like two locations portable so that we can move the UE. So we started the base stations and then we connected the portable location 1 to I6 base station and the sheep UE to the Wilson Hall base station. So these since the base station is doing beam forming and these beams are kind of parallel to each other, what we did was initially that when we started collecting the data, the portable location 1, basically this was like running. So we have it running, and then at this instant, actually, we connect this sheep farm UE to the Wilson Hall base station. And then we see here that there is like not much change actually, like immediately. It is basically I mean, this one is kind of almost achieving the same capacity as it was. And if we kind of stop it, actually the sheep farm is having the same capacity. Then what we did was that we stopped this location, and then connected portable location 2 to the I6 base station. So here we can see that we had the portable location 2 working. So again, kind of it's the similar curve. It's showing here actually. So at this instant, we connected the sheep farm UE actually, right? So we are, I mean, it is achieving lower capacity at this moment now. Compared to the previous one. And the moment we stop the portable location 2, then the sheep farm UE achieve capacity kind of increases. So that's basically because this beam was interfering to this beam. And since they are not coordinating with each other, or on some of the RBs, actually, right, they will be interfering, and that will result in reduced system performance. So for the same location, we also connected this UE, so the Curtis Farm UE. So here we can see that, I mean, it didn't have any like significant impact like we can see in this one, because again, like these beams are more or less parallel to each other. So the interference from this this beam will not affect the UE in like in the other base station, but it will affect this UE. So this needs kind of careful scheduling and careful user grouping actually in multi-cell mMIMO settings. And those kind of algorithmic studies can be performed on this system, or I mean the performance characterization studies as well. These were some of the results that were captured through this campaign through using these APIs. We have some more results. We have this design and implementation of Era Wireless Living Lab for rural broadband and applications paper. This covers like a lot of details about the Era, how it is designed, how it is implemented, what it has to offer. You can check this article. We have the AraMIMO. some of the results basically that we showed on the previous slides are reported in this AraMIMO paper. We have the SDR, we have another paper, AraRatch, and then we have the open source 5G core, AraSync, and like similarly other papers. You can check them out. And if you have any questions or anything, you can reach out to us, and we can certainly work with you to help you basically in you can use the this platform for your research. Here are some of the resources. So the portal is available at portal.arawireless.org, and this is what I accessed actually when I was doing the experiment. Here is our user manual. So we have the arawireless.readthedocs.io. If you want to reach out to us, if there is anything that you want to share with us, any capability that you want, or I mean, if you want kind of to do some research or create your account, register your account, basically you can follow the user manual, or you can reach out to us at e2@arawireless.org. We also have user groups that you can send your queries to at era-users@googlegroups.com. And we also hold office hours that are on Tuesday, 5 to 5:30 p.m. US Central Time. That is UTC -6. So if you want to have a live chat, you can join our office hours as well. And then if you have any, I mean, if you are doing experiments on our platform and you need any support or anything, you can reach out to us at these two email addresses. So that's all from the from my side. Actually, if anybody has any questions, I would be happy to answer them. Yeah, over to you, Jay. Are there any questions? Let me... Okay, looks like Jay is not here. Let me see if we have... Ali, are there any questions to be answered?
In the chat box, there aren't yet. If anyone would like to ask something, they can.
Okay. Yeah. You can either post your questions or you can raise your hand. You can ask as well. If there is any question, I would be happy to answer. Okay, looks like Brijesh has a question. Ali, do you need to unmute him or?
Yeah.
Okay.
Okay, fine. Yeah. Hey, hi, Taimur. Thanks for the presentation. Yeah. So my name is Brijesh. I am at the Ohio State. So just a quick question regarding the demo that you showed, right? Again, excellent work. Just a clarification question. So you showed a statistics of UE, right? So in that demo, it was static, right? With respect to time. So just curious whether those UE stats vary with time.
Oh yes, they do. That's because I mean I just ran the command. It just output the very current basically like achieved performance. So it will just return that. But basically in the scripts that I showed actually, right, and that basically you can collect the data basically, let's say every second, for example. So yeah, it varies with time definitely.
I see. Oh, so and the granularity is 1 second, right?
Yeah, so currently basically we can have it 1 second. I mean that's basically the system performance through the wrapper APIs. But if we let's say want it per RB or per channel, I mean kind of that can be, I mean either achieved through the CSI metrics or the user grouping info as well. So that has basically kind of that can give you like per frame as well. For example, for a group of users in a particular frame actually, right? How much like data rate was achieved, for example, or what was the orthogonality metric actually at that particular moment. So that that granularity can also be achieved. But for the wrapper APIs that I showed today, actually, right, the granularity is like 1 second.
I see. Okay, yeah,
Yeah.
that helps. Yeah, and just a follow-up question. So this UEs that we have, they are mobile, right? Or not all?
Not all. So most of them are like fixed UEs
I
actually.
see. Okay.
Some of them are mobile. So we have a mobile UE on a bus actually, the SciRide bus actually that operates here, and then we have one over the it's like basically a fire safety kind of like vehicle stuff, and then we have some of the agrobots, right? So agrobots actually tractors. We have like a mobile UE.
Mhm. Okay, sounds
Yeah.
good. Okay, that helps. Thank you so much.
Yeah, you're welcome. Okay, we do have some time left. Any other questions? Okay, I think there is one question in the chat. For the AraMIMO, when running on the container, do I run as a base station or UE or both at the same time? I know what base station is based. Okay, so yeah, that's a good question. So you can reserve both the base station and UE. So by default, so this is kind of like AraMIMO, like this platform is based on a commercial system that's like from the Skylark Wireless. So by default, actually the base station would be running and the UEs will be connected to it. So if I mean in today's demo, I logged in, I basically launched a container on the base station, and there I could see the UE stats and everything because it's basically collecting those stats. But what you can do is you can reserve a UE node as well, and then you can basically launch your container on the UE node, and then even maybe you can disconnect a UE, or you can change basically the frequency, or I mean whatever you want to do with it. So if you have an experiment that needs both access to the UE, for example, just like the grouping experiment, if you want to some UE to be disconnected and some remains connected, so you would have to reserve them, right? So that other users are not doing experiment on it, and then you are not interfering with someone else's experiment. You have to make sure that you have reserved it, and then basically you can play with it actually. So you can play with the base station, and then you can play with the UE as well. I hope that answered your question. Okay. Do we have any other question? Still have a few minutes left.
Okay, I think if there are no other questions, I would like first to thank you, Taimur, very much for your presentation and demo, and everyone attended, actually. Thank you for attending. And as Ali mentioned in chat, this is recorded webinar, so it's going to be published into our YouTube channel. And also, as Jay said at the very beginning, we have a series of webinars coming up every month, one webinar. So please check our LinkedIn page for all webinars, and also we presented the QR code at the very beginning of this presentation. Thank you, everyone.
Thank you, everyone. Thank you for joining.
Thank you.